So welcome to block number 4, which will be devoted to classification and all the related topics. In contrast to the previous 3 blocks, it has only 2 learning sequences. In the first learning sequence, we are going to talk about some basic things, what classification is, what kinds of classification exist, and so on, how to evaluate classification models. And we will also consider several state-of-the-art classification methods. And in the second learning sequence, we are going to talk about how to use projection-based methods for classification. Okay. So let's start with a very simple thing, what actually classification is. There are many different definitions you can find also on the internet, but one of the definitions, which probably not very straightforward, is that classification allows you to get answers to the questions that you see on this slide. For example, how to distinguish between genuine and fake medicine, how to find out glass type or glass type, or if metal oxides content is known, right? How to recognize a temperament of a person knowing answers to a questionnaire. So you can see that in all these cases we use specific verbs like distinguish, find out, recognize, and so on. So we can sort of summarize this by creating our own definition. So classification is when you have some individual measurements which can be assigned into groups. So that's actually what classification does. It allows you to arrange different observations, different measurements into, for example, 2 or several groups. Okay. How it does that? It of course by using features, like we do it also for PCA and for regression, for example. So we simply look at the feature values and we try to find analogy in the common behavior of these feature values. Okay. So now let's talk about some details. And first of all, I would like to present a geometrical view, how we can sort of show the classification task geometrically. You remember we already used this representation, geometrical representation of data. We call it a variable space, where every variable is, or every feature is an axis in the space of this space, and then observations are points of the space. For example, we have 2 variables. In this case, we have 2-dimensional space, and then every observation is just a point in the space. Then you can see that we have clearly 2 groups of observations. So the red points and the blue points are sort of clustered close to each other, right? So the red points are in one cluster and the blue points in the other cluster. So how we can define a class? So from the geometrical point of view, class is a subspace. And there are several ways to do that. For example, we can simply split the whole plane to 2 half planes. And then we have a discrimination line. So if point lies on one side of this line, this point will be considered as a member of one class. If point is lying on the other side, it will be from the other class. So this is what we call the discrimination. So we discriminate the whole variable space into 2 half planes, half spaces, right? The other way to do that will be, for example, to define a closed subspace. So it's not a half infinite like half plane. For example, we can use, in this case, we can use circle or ellipse, or maybe a sphere if we are talking about 3D. In this case, we simply define a class as a closed volume. So if point is inside this volume, the point is from the class. If point is outside the volume, the point is outside the class. What's the principal difference between these 2 approaches, and also how to implement these approaches mathematically? That's what actually this learning sequence is about. In all these cases, it doesn't matter which approach we use a kind of similarity measure. So we can say that 2 points are similar. We measure how 2 measurements are similar. Yeah? And there are several ways to measure the similarity. We are going to use a distance measure. So we measure a similarity as a distance between 2 points, 2 observations in variable space. And we know that, of course, we can compute distance in many different ways. So, but in general, as soon as we define which distance we use, we measure similarity simply as a distance. Okay. There are also methods that are based on non-distance approach, for example, probabilistic approach. But in this particular block, we are going to talk about only distance-based measures. Okay. Now, if you consider all classification methods, all classification tasks, they can be divided to unsupervised and supervised. What's the difference? Well, the difference is in several things. First of all, is what we actually have as an input. So what kind of information we have at the beginning, and then what's the aim, and then how we do that. Okay. For example, if we talk about, let's say we know only number of classes, but we don't have a training set. So we have some observations, but we have no idea which class actually these observations came from. So in this case, we need to use unsupervised methods because we simply don't have enough data to teach our model for recognizing different classes, right? Sometimes we even don't have a number of classes, but still need to sort of to classify, to group our observations into groups, right? Divide our observations into groups. That's actually aim, right? So we need to divide our observations, our measurements into two or several groups, which we call classes. And then the idea is we simply look for analogies, we try to compare all measurements to each other, and then we try to find out the similarity and dissimilarity measure, and then use similarity and dissimilarity measure to sort of combine to cluster the measurements together, right? So these are unsupervised methods. And probably one of the most known unsupervised classification that at least chemical students know, it's the table of elements by Mendeleev. And you know that there are several ways to cluster elements depending on different features, different parameters of these elements, right? For example, we can think about metals, non-metals, and so on. Okay. Another very topical nowadays, at least at this time when I record this video, clustering example is how the coronavirus developing, the genome of coronavirus developing. So you can see, for example, this is a hierarchical clustering I got from this Next Strain website, which is actually collecting this information from different sources and then make a show this developing of the virus. So we can see that we have actually several branches or several strains of virus, and then we know that it's caused by mutations in time. Okay. You can also remember the example with correlation table from the PCA part. And then you remember that when we make actually correlation table, this is how it looks like, the original table, right? So it's just it has the same order of rows and columns as we have in our data set. But then what we can do, we can cluster the rows and cluster the columns to produce a bit better a better overview. For example, in this case, I only cluster it rows. So look at this. So now you can see that, I mean, this is a one big cluster of rows. This is a second big cluster of rows, right? Then we have this cluster of rows. And if you actually cluster both rows and columns, you can see this is the feature. So you remember this clear pattern. So we have one big cluster here, and then we have a smaller cluster here, a smaller cluster here, and then we have an IQ as a separate sort of cluster, right? So this is another example of clustering. We didn't provide any information about which variables are similar, not similar in terms of correlation values, but we were able to combine these variables together into groups by similarity. And then sometimes, however, you have this training set. So what do I mean by that? You have measurements from different classes, right? For example, you know that these measurements, these are spectra from apples and these are spectra from pears, for example, and then you can actually classify apple or pear by measuring another spectrum, right? So when you have this observation with known classes, you can train your models, and that's why we call this supervised methods, because you can supervise your model to find what makes values of features taken from different groups or from same group similar or dissimilar. Okay. So the aim in this case is a classification of new measurements, and then how we do that, we simply train a classification model. So that's the supervised methods. And then supervised classification can be done in two different ways. You either make a discrimination or you make one-class classification. So let's talk a little bit about that. So first of all, the one-class classification, it's shown on the left part. In this case, you make a class, you define a model or a class for every group, for every class you have. Okay. In this case, you can see I defined the classes as a closed volume. So in this case, it's just an ellipse. And then the idea is that you have as many models as many classes you have. Classes may overlap in this case, so you may have objects that are similar to several classes, for example. And of course, there can be also object in between, right? For example, if you have an object here, it means that it doesn't belong to any classes at all. Okay. In case of discrimination, you discriminate objects, so it means that you don't have other possibilities. So object should belong to one of the classes you define. So it means that you have only one model, regardless how many classes you have. And then classes in this case will never overlap, of course. And of course, in this case, you don't have a possibility for identifying, for example, an outlier object which does not belong to any class. Okay, so that's what we call a discrimination. We will consider both one-class classification and discrimination. I'll show you a couple of state-of-the-art methods for that, and also in the next learning sequence we will consider project-based classification, one-class classifier, and discrimination methods. So that's the short introduction. So summing up, we have actually 3 subtasks. When we say classification, we usually use it as a general word, but actually we can also define it into smaller subtasks. When we arrange measurements into groups without actually knowing any a priori information which groups they belong to, that's what we call a clustering, right? Clustering is unsupervised technique based on simply measuring similarity, dissimilarity between measurements. If we assign an observation to a certain class, that's what we call the one-class classification. So in this case, objects can belong to the class or not belong to a class, and if you have several classes, they can belong to several classes as well, or they can be outliers, so it means do not belong to any classes at all. And then discrimination is when we do multiple classes classification, so it means that we make one model that tells which class your object is from, your measurement is from, without possibility for overlapping. Okay. Very often there is another term that sort of combines all these subtasks together. It's called pattern recognition, so sort of recognize patterns in the behavior of your features.